Hello and welcome to the Chapter 2 podcast on Section 2. Here we're going to talk about some of the basics of atomic structure and some of the history behind the discovery of their particles. When we last talked a little bit about Dalton's atomic theory, he had an idea of what the atom was, and his model was essentially that the atom was like this indestructible ball, if you will, that were basically just different for each element. His results were circumstantial and they were based upon ratios in which elements combine to form compounds. During his time, again, there was a severe lack of technology, and as the turn of the 20th century began, there was this thing called electricity that people began using for their experimental studies. So the technology change really allowed for a more thorough examination of what Dalton believed what the atom was. Through this process, and some of the key experiments we're going to talk about in this podcast show that atoms have a very complex structure, and that it wasn't just this black ball, that there were particles that made up smaller particles than the atom itself that made up each individual atom in terms of charges and subatomic particles, some of which you probably already heard of. And we can actually see atoms now using scanning tunneling microscopes, and so the image on the right is an example of that. What they began to do is they began creating cathode ray tubes, and cathode ray tubes are basically, as you see on the bottom of this, these glass tubes where they would trap gas in, and then you'd have electrodes connected through. The rationale was that they were able to begin to identify elements or isolate elements by running electricity through compounds. So they wondered if they would see anything if they ran electricity through elements. So these are partially evacuated tubes, and what they would find is that as they would trap elemental gases inside of these tubes, they would get this ray known as a cathode ray. And it didn't matter where it came from, it was always the same. It always originated from the negative electrode and traveled from cathode to anode. And basically, it was invisible, but when they added a material to the tube itself, they began to see the beam itself. So were cathode rays? Were they particles or were they radiation? What they found is that they were deflected by negative electric fields, and they also found that it was ubiquitous, which basically means that no matter what kind of gas, elemental gas, they trapped inside of this cathode ray tube, they would see these rays show up no matter what. The person who first came up with this was Crookes, but another person, J.J. Thomson, made an even more important contribution. So this handsome fellow you see here on the right is J.J. Thomson, and basically he was analyzing the nature of these cathode rays and was basically able to quantify the effect of these magnetic fields on these particles that he later termed electrons. So not only identified the nature of the charge, but he was actually able to determine the charge to mass ratio for an electron. So he found it was a certain number of coulombs per electrons. Coulombs is a measure of charge. In chemistry, we won't use coulombs too much, but if you're going to move on to physics, that's something you should be more familiar with later, especially if you're going to study electricity. So now that J.J. Thomson had found the mass or charge to mass ratio of an electron, all someone had to do next was either find the charge or the mass of an electron, the exact charge, and they would be able to figure out exactly what the mass of an electron really is. This other guy, Millikan, came up with an ingenious experiment to actually figure out the charge of an electron, and he did this using oil drops. This schematic of his setup is here below his handsome picture, and he basically figured out what the charge of an electron was. What he would do is he would have this spray that would give out very, very fine droplets of oil. Okay, and as these fine droplets, what he would find is as they pass through ionizing radiation, these oil droplets would pick up electrons and become charged. And as they would fall between magnetic plates, they could measure the effect of the voltage on these charged droplets. And it was always this certain multiple, and that multiple ended up being the actual charge of the electron. Once they were able to figure out the charge of an electron in coulombs, they were showing that the mass of the electron is 2,000 times smaller than the hydrogen atom, which implied that there's a lot of missing mass that isn't accounted for just by identifying electrons. So there must be other things present. Also, they knew that all elements were electrically neutral, which means that if there's something negative, like an electron present inside of the atom, there has to be something to counteract that, which kind of gave rise to the idea that maybe there's some protons. But to kind of take it a little aside, they were using a lot of radioactivity, and this was another new technology that was emerging with, along with electricity. Radioactivity, they didn't really know a whole bunch about it at the time, but its origins come from a French chemist by the name of Henri Becquerel. He had this rock in his lab that would expose his photography film that he hadn't even used yet. He eventually figured out the rock was emitting radiation on its own, or energy on its own, without a chemical reaction driving it. Okay, so he wanted to know what was in this rock that was the source of this, what he called radiation. So you can see Mr. Becquerel, his fabulous beard. He had two students in his lab, the Curies, Pierre and Marie, who you see down here, who basically took that rock and many like it and basically broke it down and isolated the elements inside that were the source of the radioactivity. They isolated two new elements, polonium and radium, and earned the Nobel Prize for their findings. And they were one group that began to study the effects of radiation on things. Another fellow who did it was a guy by the name of Ernest Rutherford, who was actually working in J.J. Thomson's lab at the time. He was studying the different kinds of radiation that were emanating from polonium, radium, uranium, and other radioactive isotopes. There's alpha radiation, which they knew at that time had a +2 charge and was heavy. They had beta radiation, which had a -1 charge, and they later identified it as a fast-moving electron. And they also had gamma radiation, which had no charge and was pure electromagnetic radiation. In one of his classic studies, they would run these different kinds of radiation sources through a little hole to kind of concentrate it into a thin beam, and then expose it to radioactive fields. And of course, the beta rays would be attracted to the positive field, the alpha rays would be attracted to the negative field, and then the gammas would go straight through because they weren't attracted to any sort of charge. So they began to employ these forms of radiation as tools to kind of help them study the building blocks of the atom. And we'll spend more time later in the course discussing nuclear chemistry. So if we rewind back, Thomson identified the electron, and we found out that electrons actually make up a very small portion of the atom in terms of mass. So there had to be protons or something positive present. They also knew at this time that that atoms were mostly open space, and according to Thomson, based upon what he found, it changed Dalton's indestructible black ball model into what they call the plum pudding model, where there's this ball of positiveness, and then kind of spread out around inside were these electrons. They used to call it the plum pudding model, but no one knows what plum pudding is anymore. But if you can imagine like a ball of chocolate chip cookie dough, the dough would represent the positiveness in Thomson's model, and then the chips would be the electrons. But just because you say this is the model doesn't make it so someone had to actually test this. So Rutherford, who was actually working in J.J. Thomson's lab, set in motion an experiment to test whether this was really true or not. This is a schematic of Rutherford's gold foil experiment. I'm not going to get into it too much, but basically he shot a beam of alpha particles through a sheet of gold that he pounded into a few atoms thick. What he found and what he expected was the beam to go straight through, since the alpha particles are much smaller than the gold foil atoms in comparison. So you're shooting tiny subatomic particles at a giant atom, which should be almost all empty space. And this green stuff you see surrounding it represent radioactive detection paper, which would tell us where the beam of alpha particles were going to. What he found is that while the majority of the beam did go through, you would get these weird deflections at different angles, even coming back towards the source. In his original paper, he talked about how surprising this was. He said it's something like if he shot a cannonball at a Kleenex and had it bounce ricochet back at him, that's how surprising the results were to him. What you see here next to the gold foil experiment basically is a mock-up of what was actually happening. So these alpha particles were mostly running in the empty space, but a few of them were hitting something very large and very dense in comparison to the alpha particles, which we now know is the nucleus. So what we learned is that there must be something concentrated and positive, and the atom still actually is mostly empty space, which apparently is where the electrons were going to be occupied. So the implication is that the nucleus was positive, but the particles still hadn't been identified yet. Rutherford, again, in his prolific run of experiments, identified the proton through a modified cathode ray tube experiment, which is kind of summarized here. What they found is that in opposite directions, if you extended the tube, you could see an additional set of beams moving in the opposite direction, and those ended up becoming protons, which they called canal rays at the time. The neutrons, so after they discovered the protons and determined its mass, they realized that there was still mass unaccounted for, which led rise to the discovery of the neutron, which was a little bit harder to kind of isolate. But Chadwick, in an ingenious experiment, basically did a modified version of the gold foil experiment, where instead of using gold foil, he used paraffin wax. And what would happen is the neutrons would actually get stuck in the wax, and the protons would go through. So that's how he was able to identify and isolate neutrons and determine their mass. And we'll talk more about this. And until next time.